Okay, so let us start our lecture 2 of advanced quantum physics. So basically we discussed two laws, Rayleigh-Jean's law and Wenn's law in our previous lecture number 1. Today we will discuss furthermore, we will start from Planck's. So there is a problem in Wenn's and Rayleigh-Jean's. As you already know, Wenn's tell us about the energy density at lower wavelength. Moreover, Rayleigh-Jean's tells us about the energy density at higher wavelengths. So no law is tells us about the energy density at both wavelengths, means higher or low both. So there is a contradiction, means there is a problem in Rayleigh-Jean's and Wenn's law. So to solve this problem, Planck's comes. So Planck's basically solved the problems of Wenn's and Rayleigh-Jean's. Okay, basically what Planck said matter is variation, means matter is not a fixed thing, means matter changes everything, means changes its position, changes all thing in its. So matter basically changes continuously, they variate, okay, not continued but discrete. This is the main factor that the Planck tells us about that the matter's variation is not continuous, means it's discrete. Okay, as I told you already that what is discreteness. Okay, so discreteness, you already know that if energy level is 1 and particle is in energy level 2, so it must be either on energy state number 1 or energy state number 2, nor between 1 and 2. So this is basically discreteness, and Planck's called this energy as packet of energy. Okay, this is the main factor. Planck said that this energy is a packet of energy, and he derived a formula E equals to h mu, where h is the Planck's constant and mu is the frequency. Okay, so if you want to find the average energy of radiation, so if you take the average, so you know summation n equals to 0 to infinity. If you are taking for n number of particles, so nh mu, basically formula is h mu. So if you are taking n number of particles, so nh mu exponential power minus nh mu divided by kBt, divided by summation n equals to 0 to infinity exponential minus nh mu divided by kBt. Okay, so if you take LCM of this, you will get this expression. This is the basically and final expression for average energy of radiation. Radiation means average energy of every electromagnetic radiations, mean every light. So this is basically, you can say, the energy of light. Average energy of light equals to h mu divided by e power, means exponential power h mu divided by kBt minus 1. Okay, this expression gives an exact fit to total experimental distribution. So basically, when you plot a graph of this average energy, you see that you will find the exact experimental graph, mean exact experimental values as we did before. So Planck do the perfect thing, means he drive the relation correctly. Okay, so if you want to find the energy density, you already find the energy, but if you want to find the average density, here Planck's derived a formula. Here is simple a relation, you just know this relation, you don't need to drive this relation. So here is the energy density formula, 8 pi mu cube divided by lambda square into multiply h mu divided by e power h mu divided by kBt minus 1. Okay, this expression is same here, but before a new factor came, which is 8 pi mu cube divided by lambda square. So this is your energy density formula. So results of Planck same as experimental. As I already told you, Rayleigh-Jeans and Wenn's do some experiments, and their values are not equals to the experimental values. That's why both laws fail. Then Planck's came, he resolved this issue and he derived a relation of average energy, and once he plot this energy, he will get the same value, same results as experimental. So basically we can say Planck's law is perfect for energy of radiations, means energy of light. Okay, So basically, what is the next concept? A little bit about photoelectric effect. What is photoelectric effect? Photoelectric effect is basically a concept that you have to take two electrodes, means one is anode, positively charged, and one is cathode, negatively charged. You have to connect your electrodes with external battery source, and you have to fall photons, means light, onto metal, onto your anode electrode, means onto positively charged electrode, which is anode. It is a metal, and photons you have to fall on it. Once you fall photons on anode, you see that electrons start emitting from this anode. And these electrons you already know has a contribution of negatively charged. So cathode is also, what is cathode? So these electrons are negatively charged, so it start moving towards cathode. Okay. So the amount of photons you fall on anode, the amount of electrons start emitting. But there is a suitable amount of frequency of this photon. Okay, if you achieve this suitable amount of frequency, then the only photon electrons start emitting. Otherwise, these electrons not able to emit from anode. Okay, so this is basic concept of photoelectric effect. So photoelectric effect basically, electron, you already know that electron is a particle always eject by particle. So this experiment tells us about the particle nature of photons, means light, particle nature of light, because how these electrons start emitting, this is the main question in photoelectric effect. We know electron has a mass. Okay, so electron is a particle, photons has no mass. So classically, this is not a particle, but a thing is only ejected when there is an interaction between two particles. So if this photon is a particle, this is already a particle electron. If this photon is a particle, this is the only chance these electrons will start emitting. So electrons are start emitting, we see, so we can conclude that these photons are also particle in nature. So that's why we are saying particle always eject particle. Okay. So from this experiment we can say that light, we can say that particle nature of light. Okay. This packet is called photons by Einstein. Photoelectric effect experiment was performed by Einstein. Okay. And he names this light packets as photons. Planck named them as packet of energy. Okay. But Einstein gave the name of light as photons. Okay, so here we all did, but the next thing is to confirm this experiment, either Einstein's experiment is correctly perfect or not. So we have to do another experiment to just confirm the photoelectric effect Einstein's experiment. So what is this Compton scattering? So Compton scattering is basically an experiment in which you have to take an electron which is at rest, and you have to fall an incident photon with a frequency of lambda I. Incident photon with a wavelength of lambda I. Okay. So you already know that photons have some mass. Photons do not have mass, but we already see that in photoelectric effect that photons show particle behavior. So here photons are also behaves like a particle. So suppose this is my photon, it strikes on electron. So particles are basically hitting towards particle. So what should happen? This is a practical example like in our daily life, like snooker ball. One ball is white where you hit with the cue, and the other the ball hits. Okay. So there is two things in snooker ball, two balls that hits, one ball move other side, the other ball move towards the other side, because both balls are particles, and when there is an interaction collision between particle, both balls will are in their direction, either opposite, either random direction. So same thing happens here, because photon light, this is light, is a particle, and this is also a particle. When light falls on this electron, when they collide, you see after result that electron move this direction, scattered electron, and your photon means light move in this direction. So how this possible? This is only possible if both things are particle. If both things are particle, when they so this will be happen. So for this experiment, we conclude that our photon, incident photon, is also behave like a particle in nature. Okay, so this experiment confirms Einstein photoelectric effect. Okay, so there is no more need to confirm this experiment. So here is a relation of Compton scattering. You must have to know this formula. You have to use this formula in your numerical solving problems. Okay. So lambda, delta lambda, which is also called lambda Compton's shift. Okay. Compton shift basically equals to lambda f final wavelength minus initial wavelength, which is Compton shift delta lambda final minus initial. And this delta lambda basically equals to h divided by mc 1 minus cos of theta. Okay, so quantum scattering confirmed quantum concept. As I already told you, there is no need to confirm. Already told you about that. Quantum scattering confirmed all the concepts of quantum. Okay, so here we perfectly say that light behaves. So light behaves like a particle. Okay, either it has no mass. Light photons has no mass, but it behaves like a particle. Okay, so next concept is de Broglie. De Broglie is a new scientist. What it he says. So let us suppose what if particle behaves like a wave. Okay, you are understanding? We discussed before. Light behaves like a particle. Light is a wave. Basically, wave behaves like a particle. We did in these experiments. Waves behaves like a particle. Now imagine if particle behaves like a wave. So this concept was introduced by de Broglie. He is the Prince of France. Okay, he discovered this thing that wave is behaving like a particle. But how if particle behaves like a wave? So let us check. So de Broglie used the concept of Planck's quantum. De Broglie used just the concept of Planck's quantum. Already you know what is Planck's quantum energy of photon E equals to h mu. So he take the same concept A equals to h mu. What he did next, he just put the value of frequency here, mu. You know v equals to f lambda, f basically becomes equals to v by lambda. And what is this v? V is basically the speed of light. So you just convert it c divided by lambda. So your expression becomes equals to E equals to hc by lambda. So this is the relation of the Broglie wavelength. Electromagnetic radiation has a wave nature. Okay, so if you are increasing wavelength, energy will decrease. If energy will increase, wavelength will decrease. Inverse relation between energy and wavelength. So this is the relation of the Broglie wavelength. Okay. So now move towards next. So here you see that formula is E equals to hc by lambda. Lambda. What is this lambda? Lambda is the basically wavelength. Wavelength only some ones have if they are wave in nature. So electromagnetic radiations means photons, means they are particles. So particles are getting relation in lambda. Are you understood? Particles E means energy of photons, means particles energy, getting the expression in lambda means wavelength. So here we conclude that particles behave like a wave. Like photons, lights also behave like a wave, but they also behave like a particle. So here we conclude that light shows dual in nature. Light have both the properties. Light is a wave, light is also behaves like a particle. Light is dual in nature. Okay. So de Broglie next take the Einstein's expression E equals to hc by lambda. Okay, E equals to hc by lambda. He just compared his previous relation, Planck's relation, with the Einstein's relation. He just compared the value of E. E is the mc square and before hc by lambda. Okay, once he cancels with this c, you will get mc becomes equals to h by lambda. So here mc, what is mc? M and velocity mv, you know, it is the basically momentum. Whose momentum? Momentum of photon means momentum of light. So here you also see that momentum of photon means momentum of particle, giving expression in lambda. So you also see that our particle also behave like a wave in nature. Only waves have the wavelength lambda. Here particle, here wave. Here you can say particle behave like a wave in nature. Okay. So it mv becomes p equals to h by lambda. Understood? Okay. So this is the generalized expression of Einstein and Planck's by de Broglie. De Broglie basically combines the both relation of Einstein and Planck's and get the final relation p equals to h by lambda. Okay. So if you find the wavelength of electrons, so let's take an example. Lambda, you know, as p equals to h by lambda. If you want to find lambda, so lambda becomes equals to h by p. H by P. And P is basically mv means mc. Put the value of Planck's constant, you know, which is 6.65 into 10 raised to the minus 34, and mass of electron 9.1 into 10 raised to the minus 31 into 3 into 10 raised to the 8, which is the speed of light. After calculating, you will get your answer 2.4 into 10 raised to the minus 12 meters, which is measurable, which is suitable. We can measure this wavelength, but we cannot measure this wavelength. 22 into 10 is to the minus 44. Minus 44 is very small wavelength. We cannot find. We can only find the wavelength having range 10 raised to power minus 18. No more than. Okay. So this is the limit. So next thing is, we know that electron is revolving around the nucleus. So Bohr next came, new scientist after de Broglie. We already know that electron revolves around the nucleus. Nucleus is circular in shape. So circle has a circumference which is 2 pi r. So circle has circumference, I am denoting by L, which is equals to 2 pi r. Because this electron is a particle, so before we see that, already discussed that a particle behaves like a wave. Every particle in nature are associated with wave, means they are emitting waves. So this electron is moving in the nucleus and it is continuously emitting waves. We don't know what is the wavelength of that wave, so we are just taking lambda. And why n? Because they are emitting n number of waves. We don't know how much waves they are emitting. So basically 2 pi r basically equals to n lambda. Okay, 2 pi r equals to n lambda. And here is the relation of Bohr. We already discussed this in 10th class, that mvr equals to nh by 2 pi. This is the Bohr relation. Here you take the value of Bohr relation. So you just have to put the value of 2 pi r equals to n lambda. 2 pi move towards upside and 2 pi r becomes equals to n lambda. N lambda mv becomes equals to nh. Okay, after substituting you will get your final relation, which is this. Okay, 2 pi r equals to nh by mv. You can also say that to mvr equals to nh by 2 pi. Okay, so this is your final expression of Bohr's law, how to derive this. Okay. Another method is that you already know that circumference becomes equals to n lambda, and you already derived upside that momentum basically equals to h by lambda, and lambda becomes equals to h by mv. So just put the value of this lambda here. So 2 pi r becomes equals to nh by mv, and this mv goes up, 2 pi move to downside, you will get the Bohr relation mvr equals to nh by 2 pi. Okay, so our last today's topic is double slit experiment. What is the double slit experiment? Double slit experiment is that you have to take incident photons. Up there are a slit which has two holes, slit 1 and slit 2, and here is a screen where you see the results. You are following waves initial with a wavelength lambda. You will see these waves are hitting this slit and it emits waves, and these photons are also striking towards second slit and it also emits waves. And you will see on the result screen, means on your recorder, you see that there are bright and dark fringes just comes. Okay, so when you plot, you will get this graph. So these are basically intensity graph where you get peaks. This here is constructive interference, means bright fringes, you will see bright light here, and where is low peaks, here is the destructive interference, means here is dark spots. Understood? So if electrons, so quantum interference. If you are falling electron, so there is quantum interference. So this is basically, so for electron you can say it's basically wonder of quantum physics, means there is tunneling. Okay, there is basically tunneling. So next thing is basically some applications of quantum mechanics, like they are using in GPS system, global positioning system, chips of circuits, means mobiles, laptop, everything's MRI. Okay, magnetic resonance interference, waves associated with all particles. No particle in this world are having no waves. Every particle are emitting waves. Okay, so this is our lecture number 2. Tomorrow we will start our next lecture of advanced quantum physics. So for here, thanks a lot.